1, we're asked to show that the allele frequencies of P and Q in a breeding population with genofrequency types capital P, Q, and R are given by P is equal to P plus half Q and Q is equal to half Q plus R. To show this, we have to let capital P equal homozygous dominant, Q equal heterozygous, and R equal homozygous recessive. Now, since P represents the frequencies of heterozygous dominant capital A shown up in a population, then P has a 100% chance of producing a homozygous dominant, and Q has a 50% chance. So, P would equal capital P plus half Q, since it is a 100% chance of homozygous dominant and a half chance of a homozygous dominant. And since Q represents the frequency of heterozygous recessive in a population, then Q has a 50% chance of producing homozygous recessive, and R has a 100% chance. So, Q would equal half of capital Q plus capital R, or Q would equal half of a heterozygous plus a homozygous recessive.
Problem 2 says, to find the frequency of allele A in the adult population if a homozygous dominant type egg has a probability of 0.8 of mating and a homozygous recessive type egg has a probability 0.2 of mating, but a heterozygous type egg has a probability of 1.0 of mating. So we decided to look at this problem through the Hardy-Weinberg principle. So that means P equals P plus 1/2 Q, and Q equals 1/2 Q plus R. And overall, P plus Q equals the population as a whole. That being said, as we plug these numbers in for P, R, and Q, P equals 0.8, R equals 0.2, and Q equals 1. So, as we go along, that means the frequency initially will be 1.3 for P, 0.7 for Q, and overall 2 for Z. Now, to find the actual frequency, we will have to take P over Z and Q over Z, multiply it by 100 to get the percent. So, at the bottom of the page here, you can see for capital A, we take 1.3 over the whole 2, multiply it by 100, and get 65%. To check this, we will also have to find little a, which is Q over Z, meaning it would be 0.7 over 2 times 100 equaling 35. So in conclusion, the frequency of allele capital A will be 65%.
All right, this is Elizabeth Meister, and I am working on the genetics problem, part 3. So the question is, given the following balance equation showing stable ratios, f of p equals 0.8 p squared plus 1 times 2pq plus 0.2 q squared, and that p plus q equals 1, part A is to show that f of p equals 1 minus 0.2 p squared minus 0.8, 1 minus p squared. So to start off problem A, we'll take the original function, 0.8 p squared plus 2pq plus 0.2 q squared, and the equation p plus q equals 1. A little bit of algebra will get it equal so that q equals 1 minus p, and then you can plug that in for q in the original equation. So when q is plugged in, you get 0.8 p squared plus 2p times parentheses 1 minus p plus 0.2, and then also in parentheses 1 minus p squared. So a little bit of algebra, you can factor out the 1 minus p squared and just do some more factoring to get like a longer equation of 0.8p squared plus 2p minus 2p squared plus 0.2 minus 0.4p plus 0.2p squared. So, concised all up, you can add and subtract like terms to get minus p squared plus 1.6p plus 0.2. You can then factor out 1 plus p squared minus 2p. So then that's all also multiplied by 1 minus 0.2p squared minus 0.8. And then the 1 plus p squared minus 2p is also the same as 1 minus p, and then that whole thing squared. So that is how you get the equation 1 minus 0.2p squared minus 0.8 times 1 minus p squared. So then for part B, it is to show that the values of p, or find the values of p that maximize is f of p. So in order to do that, you have to take the derivative of the f of p function and then set that equal to 0. So there's some algebra to get the equation again to, so you can like factor stuff out and then add and subtract like terms. So then you get the equation negative 1p squared plus 1.6p plus 0.2. When you take the derivative of that, you get minus 2p plus 1.6, and then you can set that derivative equal to 0, and then subtract 1.6 over, divide by 2, so in the end, you get p equals 0.8. So that is a critical value, and then you have to use the first derivative test to see if the critical value of 0.8 is actually a maximum. So we can put it on a number line with 0.8, and then pick a term on either side. So we'll pick 0 and plug that into the to the derivative function. So when you plug 0 into the negative 2p plus 1.6 equation, you get a positive value. And then when you plug 1 into that same equation, you get a negative value. And so with the positive, and the negative, that shows that it is actually a maximum. So x equals 0.8 is the value that maximizes the function f of p.
I'm Gabby O'Connor, and I did number 4, which said, show that the maximum value of f of p occurs at p hat equals s2 divided by s1 plus s2, and f of p hat equals 1 plus s1 times s2 divided by s1 plus s2, which is less than 1. I first took the derivative of f of p, and after finding the derivative of f of p, I set that equal to 0. After setting that equal to 0, I then simplified and set 2 times s2 divided by 2s1 plus 2s2, which equals p. I then simplified that and canceled out the 2's and got s2 divided by s1 plus s2 equals p. After that, I then did the first derivative test. The first derivative test helped to determine whether S2 and S1 were both negative, both positive, or one was positive and one was negative. It was determined that both S2 and S1 were negative because that gave you a max. After performing the first derivative test, I then plugged in a negative S1 and a negative S2 into the equation f of p hat equals 1 plus s1 times s2 divided by s1 plus s2, which is less than 1. It was determined that 0.66 repeat is less than 1.
Problem 5 of the genetics problem states that assume the egg allele frequencies in the first generation are P naught for A and Q naught equals 1 minus P for lowercase a. So the genotype frequencies are P naught squared for capital A, and Q naught squared for double lowercase a. Show the frequency of capital A in the adult population after selection, and the resulting egg population from those adults is, and then it gives the formula with f of P naught as given above. So if we look at the work, the egg allele frequency in the first generation is P naught for A, and for Q naught, it's lowercase a. And then we have Q naught equaling 1 minus P naught. So to show that, our job is to show that the frequency of A in the adult population after selection is this given equation. P1 equals 1 plus S1 times P squared naught plus P naught times 1 minus P naught, all divided by F of P naught. So if we take the information from above as it says, we have that the F of A of P naught equals this 1 plus S1 times P squared naught, or P2 naught, plus P naught Q plus 0. But since from earlier in the question, it gives us Q is equal to 1 minus P naught, we put 1 minus P naught in that equation for Q, and then that gives us so that'll give us 1 plus S1 times P2 naught plus P naught times 1 minus P naught. Just like I said, putting the Q in, or putting the 1 minus P naught in for the Q. And then in order to get the ratio, we will then divide by F of P naught, and then I have that written below in terms of dividing by the full F of P naught, and then dividing by the notation for F of P naught. And we can clearly see that given the information, we can show that the frequency for A is shown by the equation below.
We believe that the quality of our answers are pretty good and accurate because if answers were estimated to this problem, they would be somewhat close to what we got. We also checked to make sure that our answers were in the right domain in context with our problem.